Welcome to webinar presentation. I'm Bill Baez with ASQ. Today with us, Dr. Jack Revelle. Dr. Revelle has been a consultant to a broad range of organizations throughout the world. He's better understand and improve their processes through the use of Six Sigma and continuous improvement tools, techniques, and methods, including lean practices. He holds a PhD in Industrial Engineering and Management from Oklahoma State University. He's the author of Quality Essentials, a reference guide from A to Z. Most notably, he's one of our most active contributors to ISQ's body of knowledge team to improve and expand one of our most popular web resources, the Learn About Quality area. In this series, Jack will be walking us through each of the time-tested quality tools featured in that area. And to get things started, today he'll be introducing our first series on the 7 quality control tools. It's a sneak peek at what you'll learn in each of the upcoming installments. Thank you, Jack, for bearing to help us launch our Quality Essentials tool series. Now let's get out of the way and pass this presentation over to you.
Thank you very much, Pablo, and thanks not only to you but to ASQ for providing the opportunity to share this information about the various quality tools to the ASQ membership, and in fact to anyone who's interested in the use of the quality tools to help them to collect data, to analyze data, to solve problems, and reduce complexity and all other things that we are concerned about. And so let's start with our introduction to what the webinar series is all about. We're going to be 4 quality tool groups. The one today is on the 7 QC or control tools. It will be followed in short order with discussions about the 7 management and planning tools, also the 7 MP tools. We'll have the 7 supplemental tools, and of course the 7 team support tools. But today, we start at the beginning at the 7 quality control tools. They are, in no particular order, data Pareto analysis, histograms, and the control charts. Let's start out with a discussion of data tables. And the best of that is to start out with an understanding of data. To begin, we need data stratification. The purpose of stratification is to convert heterogeneous population to a collection of homogeneous populations, better known as samples. Homogeneous, what we're about is groups composed of people or units with attributes or characteristics. For example, genders, ages, costs, and qualities. As opposed to homogeneous, which is composed of people or units with a similar attributes or characteristics. Part of data, of course, includes check or test. Now here's an example. Let's suppose that we have a situation, in this case what we're talking about is administrative materials, and there's 4 kinds of defects that seem to be occurring amongst our 4 suppliers, A, C, and D, listed across the top. And those defects, as you can see, are incorrect invoice, incorrect inventory, damaged materials, and incorrect test documentation. Now, this tally sheet is to make it easy as possible, user-friendly, if you will, for the person or persons who's going to be collecting the data. So when an individual is looking at the work provided by supplier A and he or she finds an incorrect invoice, they're going to put in a slash mark in cell in the column and the incorrect invoice row. You find that supplier A also has an incorrect inventory problem, a hash mark will be put in there. Or for material, or for incorrect test documentation. Do the same not only for all the defects, but for all the suppliers as well. Let's take a simple example. Continue with supplier A. We have 4 slash marks in the incorrect invoice row. We have 5 in the incorrect inventory row. Let me go. We have misspoke. We have in the incorrect invoice row, 5 incorrect in row, 3 in the material row, and 1 incorrect test documentation row. Total of 13 separate defects noted with respect to supplier A. We do the same thing for B, C, and D. We also do the same kind of data collection, some of looking across row by row. For example, for incorrect invoice, supplier A, as we've already said, had 4 slash marks. B has 1, C none, D had 2 for a total of 7. We do that for all these particular defects. And we'll sum up the total for all defects, 7, 9, 8, and 10, which sums to 34. That, of course, unless we made a math error, should be exactly the same as the total for all 4 suppliers with their 13, 6, 7, and 8 defects. Now, of course, the thing can be done very easily using our various types of computer software, but for the purposes of introducing it to or persons who are not familiar with the concept of data tables, better known as check or tally sheets, they thought it would be appropriate to present this so you can see what it looks like. You know, as we just said, we're going to see how many different defects A, B, C, and D have. Well, there, as you know, 13, 6, 7, 8, as you can see at the bottom of this particular diagram. But when we talk about data, what we're doing is we're stratifying it as to the type of defect. And as you can see, we've done it by 4 different defects. Vice versa, we may say 4 different defects that we know are occurring. How are suppliers doing? Well, we can see that 7 incorrect invoices, 9 incorrect inventory, et cetera, totaling to 34. But rather than across the board and mix apples with oranges, what we do is stratify by supplier so we can see what the contribution to the defect rate is by each individual supplier. And we have a 4-way stratification for suppliers, and in this case, a 4-way stratification for defects, with the result that we now have knowledge of where we want to attack our situation. We want to deal with the worst first. If you're primarily concerned with the most number of defects, we're going to start out with supplier A. On the other hand, we're going to be working with that has the incidence or greatest frequency of occurrence. We would look at incorrect test documentation, although in this case they seem to be fairly equally spread across the board. Very little difference between 10, 9, 8, and 7. So when using this, we would take this information and we could use it, analyze it further with a Pareto diagram or other instrument, some other tool that we would want to use to help us to get a better understanding of what we're doing and where we're going. And by the way, this is the assumption, previously unsaid, that each of those defects is of the same cost or concern to us. If a material was 10 times more important than, let's say, incorrect implementation or incorrect invoice, which might, let's say, the least important one was incorrect inventory. I'm not saying that always is. I'm just saying that as an example. Then we have multiples. One might be 3 times more important than that, another 4 times, another 10 times more important. So before we start moving out of the check or tally sheet diagram, what we want to do is to make sure that we're working on the worst first. And worst first takes us to our next tool, Pareto. We know trying to solve a problem at the same time is as frustrating as it is futile. The most cost-effective approach to problem prioritization and selection is to focus, I said, on the worst first. Identify the critical or vital few and temporarily work on the remainder, known as the many. These are terms that were devised many, many years ago by Dr. Joseph Juran, one of the giants in the history of quality. And provides us with that step-by-step process necessary to efficiently identify leading problems, defects, or errors. And here's what a Pareto looks like. It's a vertical bar chart, and this can be done horizontally. But got the bar chart with the defects that have the greatest frequency occurrence on the left and those with the least on the right. Now you might say, wait a second, what's that taller column with the O? That O stands for other. That's a grag. It might be onesies and twosies, and rather than lose that data in the diagram, what we do is we just accumulate them and say, let's leave them there until we've been able to reduce the incidence of the types of defects, in this case G, E, F, etc. And what we'll do is move to spread out or stratify that which is in the column and begin a process of that. We can see by the vertical bar for defect G that approximately just under 100 defects have occurred. In E, approximately 50. But if you take a look at that cumulative percent line and the cumulative frequency percentage over on the right, you'll see that 100 defects for G, approximately 30% of all the defects occurring. And if you go to the side of the column for defect E and move up to the cumulative percent line and make a hard right turn and go over to the right axis, you can see that goes around 50%, which means that about half of all defects that are occurring in this particular example are being contributed by defect G and E. In the presentation I make, the webinar on Pareto analysis, I go through step by step on how you can create the diagram and then make use of it to help us better understand what we need to do, where we need to go, and that now that about Pareto, think about scatter. Scatter, in this case of a scatter analysis, is to examine a collective paired, also known as bivariate, meaning two variables, data points, and this collective known as a data pool, to determine if a fitable relationship exists between the two data sets, that is, between one variable and the other. Here that I've created using data that came out of a magazine article many years ago. It's called Tarnished Wings. Diagram. I took the data they had in there. They had two separate charts, one average age of the airline fleet in years, and the other chart with the maintenance expenses per hour operation. They made no attempt to try and bring them together, but when I looked at them, I realized this had the makings of a scatter analysis. And it is I plotted them. So, for example, you can see the dot identified as D, which is Delta Airlines, and the air fleet at that time looks like it was about maybe 1.5, maybe 9.25 years in age. And if you go and look at the vertical axis, it looks their cost for expenses per hour of operation is about $360, $370 dollars. And we do think plotting the bivariate data points for each of the airlines that existed at that time. The UP was Air/Piedmont. U.S. Air had just absorbed Piedmont. You can see is Continental. Over to the far right, N is Northwest Airlines, U is United Airlines, T is Transworld, E is Eastern, and P, way out of the distance, is Pan Am. Now, everybody well knows Pan Am no longer exists, Eastern Airlines no longer exists, etc. But what we do is we start drawings in there, and I explain how all that is done in my work on the subject of scatter analysis. And we draw borders of that acute angle, and then bisect that angle with a center line, and that becomes, if you have a course in basic statistics, our regression line, our predictive line, so that if you have how the average age of the fleet in years, you can predict what the average maintenance cost per hour of operation is going to be. But in this case, you'll notice that if we take FR data, and we can see there's two clusters there. One has an axis, a center line that's approximately the same as the center line for the entire data set. The other, if you draw a line between P, E, T, U, and N, that's going to be approximately at right angles to the original center line. Now, what that? It looks like we have two separate groupings there, two separate clusters. When I did this to Boeing engineers a few years ago, they got excited about it because at that time, most airlines were actually flying Boeing aircraft. But we have great length in the webinar on scatter analysis, in addition to a rather unique application of scatter analysis to help figure out bonuses and pay scales for this person. Now, an effect analysis, also known as Ishikawa diagram, after the gentleman devised the first one, known as a fishbone diagram for obvious reasons. We have a spine in the center that moves from left to right, with the arrowhead spine touching the problem box, in this case a wrong shaft diameter problem we're running into. And what we do is we position 3 boxes above and boxes below the spine, each for one of the 5 M's and an E: machine, method, material, measurement, and environment. And then we attach all the boxes to the spine with arrows. And we use this as a basis for a discussion of what source or sources of the problem is in this particular case. And in the presentation I make on cause and effect of a specific webinar on that topic, I just at great length a particular I was involved in several years ago in helping a home builder identify a problem where they had some problems that existed before they even started building the houses, while they were trying to lay down electric lines and water lines in the basic land. Of approaches to doing analysis, and they depend on the improvement team's time constraints and of the problems that they face. These two concerns. Cause and effect analysis has 3 approaches, all 3 of which are in the web of cause and effect analysis. They are the random method, the SID, and the process method. There's one use of effect analysis technique that is really discussed, is the solution analysis. That we've gone through and identified the source or sources of a problem. We've done using force analysis and multi-voting to identify, both of those are discussed in one or more of the various that I'm doing. Identify a particular corrective action. But before we want to implement the corrective action, we want to debug it. We want to make sure that there's no negative side effects associated with corrective action. And so we'll put the potential corrective action in the corrective action box, and the process improvement team will discuss whether or not there's any negative side effects associated with the 5 and the E, the machine, method, material, measurement, men and women, and environment. Simple example, if we had as a heavy equipment operator, and that person, he or she has a bad cold or the flu, and the doctor has prescribed some medicine for them, that say on the prescription, or if it's not a drug, that you shouldn't make the equipment. If you take a particular drug, that's a negative effect that may have to do with, you could end up damaging the machine, you could mess some material, you could injure people, you could bring to destroy the environment. So we want to solution analysis as an effort to help make sure that the correction that we think is to be used is not one that's going to have more negative effects than effects. And that is in detail in the webinar on cause and effect analysis. Now we'll look at analysis. These graphs or run charts. These charts enable graphical plotting of data, and they can attribute or discrete data or variable or continuous data. And by the way, in the web do on-trend analysis, that you can use this for both the data on the same chart. Little technique that I've developed. Plot data either as averages or as individuals or counts. 2 is to ascertain the presence of either a positive or negative with the data that you've collected. And a trend chart, without a lot of computation, will give you that information. But recognize if a data point are out of specification or specs. Trend analysis has some very positive things. You know, it's not as control charts, but much better than looking at a collection of data in a table, because you can actually see the trends that are occurring, and actually got points that are out of specification. chart, the structure of what it looks like. On the axis, we can plot either time or sequence. That's the x-axis. In the y-axis, we can put the counts of the attribute or discrete data or the measurements of very continuous data. The center line represents the target specification devised by the engineers, as the red lines that represent the upper and lower specification limits. Anything outside of either of those represents a violation of the requirements. And so being out of spec, as you can see, that red dot below the lower specification limit means that you may reject that particular item that the data was generated from. Histogram. These are used to plot frequency of occurrence of either continuous data or attribute data, but within specific class intervals. What we want to do of data points, known as a data pool, into a distribution, for example, normal distribution curve, so as to the status of the process from data was collected. Now here's an example that was drawn up using QI macro. This is that was devised by Jay Arthur, the nowhere man, and it hits into Excel. If you go to Google and type QI macro, up with an offer to the 30-day download of QI macro, and it does everything that I've talked about so far, and many that I haven't talked about yet. Jay has put in plenty of templates there, and all you do is put your data, whatever data you have collected, in Excel format, and click on the type of this that you want, whether it's histograms or Pareto diagrams or scatter diagrams, whatever it may be. And in Xappo, you've got the chart you're looking for. And notice that in this histogram, we also have a superimposed normal distribution, and you can make a judgment as to whether or not the data that you've got collected in this sample is not normally distributed. And finally, we're going to control charts. Types of control charts. One is for variable or continuous data, as for attribute or discrete data. For the variable, we have two major charts that are used that we talk about in the webinar on control charts. That is the X-bar chart, which is average value, and the range, which is individual or measured value. For attribute discrete data, we have four separate charts from which to choose. One is the P chart. What you're interested in is the number of defective units. The P chart, fraction defective. The C chart, which is all about the number of defectives, which is the number per unit. Bar in our chart and see what it looks like. On the X-bar chart, again, this is for shaft diameters, and we can see that we have the upper and lower control limits plotted on. Those are not the same as the upper and lower spec limits. The spec outside the control limits, they may be on control limits, or they may be inside the control limits. Separations are discussed at length again on the subject of control charts, and I hope you go and take a look and take a listen to that. Below our chart is the art. That's the ranges, and I draw a vertical line on the top chart to the bottom chart for each of the various points, like point number 1, point number 2, point number 3. You have the, let's see if I can do this here. If we draw a line, just should be a straight like this. What we've got is a average of, let's say, 5 points is right here. And here we see the difference between the highest value in that sample and the lowest value, and we plot that. And so you can see that you've got averages and a chart of the variation around those averages using the X-bar on our chart. In later years, a lot of people have moved from the R value to the S value, the standard deviation, because we now have considerably greater facility in calculating variation using the standard deviation than back in the days when the R chart was first advised. Talked about the 7 QC or quality control tools. I'm turning the discussion on this webinar back to Pablo, who will bring it to a close. Pablo, it's all yours.
Thank you, Jack, for all your contributions to our growing body of knowledge and for providing listeners with this great overview and teaser of our coming 7 quality control tools series. I'm sure people are going to get a great value out of it. To more about Jack Revell, go to his website at revellsolutions.com. Also check out his book, Quality Essentials, which is published through ASQ in the item H1216, and you can find it on the Quality Press bookstore online. For more information on this and other quality topic overviews, we have tutorials, podcasts, downloadable templates, and webinars just like this one on our Learn About Quality area. You can also search for those in our Knowledge Center, which is asq.org/knowledge-center. And thank you again, and we hope you'll join us for our Essential Quality Tools series.